I said here, the key takeaway which I would like to conclude from this section is damping is an important parameter in vibration response prediction and restricting it to a certain levels. And you can play with the damping also as one of the parameter in mitigating the vibrations. So that we'll see later. So, just I mean, this is about how natural frequency can be predicted with different methods: equation of motion method, virtual work method, and energy method. So, I'm skipping this. This can be referred from the textbooks. And similarly, for multi-degree of freedom systems, you can express equation of motion for each degree of freedom. I mean, here, for example, you take this particular degree of freedom and the second one, and you write equilibrium equations for these, and then construct the two unknowns, and you will have two equations here. Okay, so when you solve for those, you will get two natural frequencies, and you can express these in the form of a eigen matrix. I mean, eigenvalue problem, like a minus lambda I x equal to 0, and you solve that. The determinant of that, when you solve, you will get the natural frequencies omega, and then you substitute them back into uh, the two equations that you have. Then you will get the mode shapes. So the mode shapes for these are nothing but the eigenvectors. When you treat it as eigenvalue in the mathematical terms, eigenvalues are nothing but natural frequencies, and eigenvectors are nothing but mode shapes. So these are the two modes you can see. So in the first one, both are vibrating in the same direction, and the second mass is actually vibrating more. I mean, with a ratio of 1 by 0.731. Whereas in the second mode, this vibrates in the opposite direction, whereas this vibrates in this direction. This is vibrating in the positive direction, and this is vibrating in the opposite direction. So what is this called? Mode shape means the pattern of vibration. So for example, you take any simply supported beam, the first mode will look like this, so something like that. In the second mode, you will see something like that. In the third mode, you will have another antisymmetric mode, symmetric mode, sorry. And then fourth mode, you will have again antisymmetric mode. So, so all such things, I mean, understanding these mode shapes will help you to, uh, I mean, guess which mode is more severe to you before the analysis itself. I mean, before doing the detailed analysis itself. So again, another way of predicting the natural frequency is applying the continuous systems principles from the basic physics. Okay, so the behavior of any system, I mean, which is continuously distributed, for example, a constant cross section beam or a bar. If you are interested in axial modes of a bar, then you can get the equilibrium of forces in the axial direction. When you are interested in bending modes or transverse modes, you can use Euler equations for beam and get the uh, I mean, force equilibrium and the moment equilibrium, and then express them into getting a differential equation. And this rho is nothing but mass per unit length, and this is the inertial force finally. So when you solve for these equations and get the constants by solving the differential equation, now you can readily get natural frequencies for all these beams, the first, second, and third, like that. Okay, by applying this formula. So why it is interesting? Why we have to even look at this kind of classical methods? There is a connection I am trying to bring towards the design itself. So when you are trying to deal with a shaft modeling or a transmission shaft, for example, which is mounted between two bearings, and you want to avoid certain wheeling speed. I mean, you want to keep the frequency of your shaft above the wheeling speed. So the at the preliminary stage, a quick design can be done using these kind of principles. You directly go and calculate natural frequency. I mean, what is your natural frequency requirement? You just put some margin over that and back calculate the cross section that you need to achieve that first natural frequency above certain range. Okay, so it's not that always you have to I mean, rely on FE methods, or always you should uh, go with FE analysis for each and every thing. But for this kind of beams or this kind of continuous systems, there are well documented empirical relations. Also, these constants, all the constants are derived, and you can go ahead and use Rogue's formulas or or from the textbooks itself, from Thomson itself, you will get this kind of equations, and you can get what is the first frequency, and you can find out what unsupported length you can have, minimum unsupported length you can have between the bearings or between the brackets of a tube or a duct, so that your frequency can be maintained above certain frequency levels. Okay, so that is the significance of still using these basic principles of calculating natural frequencies. So till now we have seen some fundamental ones. Now, if you see the realistic systems, it is not so easy to always adopt these single degree of freedom models, or kind of 2 or 3 degrees of freedom models, which we can manage manually, but uh, based on hand calculations. But when you come to actual problems, I mean, you may have to adequately capture the mass distribution and the stiffness distribution of the system. So you need many degrees of freedoms to properly represent it, which is not possible to handle with hand calculation methods. So therefore, what you will be ending up doing is FE analysis, which we currently most often, I mean, everybody does FE analysis for vibration analysis. So again, I wanted to summarize what is that we do as a part of FE analysis majorly. So you have your system modeled, and we can call it as a spatial modeling. So you are representing it as a stiffness, and you are representing the mass of your system, modeled it, and then you predicted natural frequencies and mode shapes, and you have fed in damping ratio and input excitation, whether it is harmonic or random, and then you are calculating a vibration response, stress and FRFs. Okay. So all the parameters of our interest are calculated here, and then we take a decision whether the stress is within certain limits or not. Okay. Then similarly, this is based on mode superposition methods. Another method is full harmonic method, where you can run the complete frequency range of interest as a sweep analysis, and then you get the natural frequencies from the harmonic sweep analysis, uh, and do detailed analysis around that frequencies for stress response. So that is another way of doing it. So now with this, I summarized sort of the basic background of how, what are the important parameters or the elements that we have to focus on, like natural frequency for resonant conditions, damping for the response predictions, and the forcing function like random or harmonic or shock for predicting the responses I mean, for against these excitation levels. And we also spoke about the modeling, I mean, the spatial modeling, that is mass and stiffness. Now we'll see in detail how the design cycle will look like for the vibration problems, and what are the parameters that influence our design against vibration loads, and we'll focus on those in detail quickly. Okay. So, we were, I mean, why the design for vibration needs attention? We already discussed them. There are many parameters. Now we have many parameters that we already summarized. So system design is one thing. So the configuration, material and processes itself is one thing, which is anyway required for any design cycle. But what exactly we have to see in that, we'll see in the next slides. Then input excitation, random or harmonic, analysis assumptions. We have lot of assumptions that we may have to make as a part of the simulations, like the boundary conditions, where to fix, how the contact should be defined, how the mass and stiffness should be modeled, what joints we should consider, what kind of kinematic joints you should model. See, the major limitation with vibration analysis software the current day is you cannot simulate nonlinear vibrations. Okay, nonlinear model analysis is still not possible, which can be only done through certain linearization assumptions, or you have to go with transient dynamic, nonlinear transient dynamic problems. But it may not be, it will be so cumbersome. So you will end up making certain assumptions. That is one key thing here. Damping is an input parameter, which again depends on several other factors. Like I said, what is the damping mechanism that is present? Uncertainties. This is the major thing which we should be focusing on. Like the above analysis assumptions. If my problem is very critical, vibration failures are recurring on my product, then I should definitely understand these uncertainties, and I should embrace these uncertainties, and with with lots of tests to be conducted, and we should characterize our system or the features that are resulting in key decision making should be understood well. Okay, so nonlinearity is also one such thing. So, so design cycle, when you look at any general product design cycle, will look the similar way. Like you have product requirements, you have preliminary design. So you first achieve, you evaluate a preliminary design with configuration, the functionality requirements. Then you analyze it. Then you see whether all design requirements are met. If not, you go for redesign iteration. And if yes, we'll see if the design is optimized or not, optimize it, and finally build the prototype and go for development tests or qualification tests. Even in vibration, design for vibration, the process would be pretty much same, but there are some elements like we were discussing about the boundary conditions and the damping as one parameter, uncertainties. So such things, how we uh, address in the design cycle is what we have to see. Okay, we'll see that in the next slides as we go on, touch upon the configuration and other parameters. So configuration, if you see how the configuration would be evolved in any design is basically to meet the functional requirements. It is not the vibration is never a functional requirement, but it is a sizing case because the component is subjected to these loads. Otherwise, the size functional requirement would be something like accomplishing a mechanism that need to do certain task. Okay, so such kind of the configuration is basically designed for such kind of functional requirements. But what we have to see from vibration perspective is you should know the operating range. For example, 5 hertz, 2000 hertz, or if it is engine mounted components, then what is my redline speed or the spool speeds of my engine? Okay, so then you should first objective should always be target natural frequencies. So after the configuration is over, now you size the configuration or the thickness of the component or the material selection. Everything you see such a way that your natural frequencies or the support systems of the your mounting locations on the component. Everything should can be designed such a way that natural frequency should be out of the operating range, so that I mean that the number of supports and the location of supports and the kind of materials that I mentioned, and similarly uh, the thickness or the component shape and layout, primarily meeting a functional requirement, but for vibration, if you have to tweak it slightly based on topology optimization, for example, if you want to optimize the topology to help the vibration requirement to be met, all such things should be taken care, okay, to maintain the frequencies above the operating range. Let's assume that your operating range, I mean the natural frequency you could able to keep away from the operating range. So still do you need forced vibrations to be looked at? Any answers on this from the team? See, I have kept my natural frequency away from the operating range, so I don't have any resonance condition now. But still, is it required to consider forced vibration?
Yeah, I think yes, sir.
Yes, definitely. Because it's not, it's even though you have kept your frequency of the system away from the operating range, your system is still undergoing the harmonic excitation forces. Okay, so it may not be resonating, but it will just see the same excitation uh, acting fully reversed stress state. Okay, so maybe you can just do a static analysis with the uh, excitation levels applied, but you should consider that as a fatigue level for you, fully reversed fatigue. Okay. What happens if your natural frequency falls within the operating range? That is critical. Why is that so critical? We already discussed that, so I'm with interest of time. I want to skip that question. So it's a resonant condition that occurs, and the response can be significantly high, and your system can fail if it is not adequately designed for fatigue requirements. So when your natural frequency is within the operating range, you should do a detailed analysis considering the input excitation, either it is random or harmonic. For those input excitation levels, you should be doing a detailed analysis, and you should ensure that your system is meeting the FET requirements due to the response. Okay. So the key takeaway is always the configuration should be designed such a way, I mean, evolved such a way that it withstands the vibration requirements. But this is the area where most often miss will happen in the design cycle, because we will focus majorly on the functional requirements in the beginning of the design cycle, and towards the end a detailed analysis will be taken up, and we'll see that our vibration requirement is not met, and we struggle hard to get the requirements met with a lot of design changes in the end of the design cycle, which may not be appreciated well. So that is the reason when you have significant vibration environment on your system, you should consider that parallelly while you are evolving it the configuration itself. Okay. So material selection plays another role, critical role. Like you have seen in the previous slide itself, uh, the fatigue requirement. Okay. So that is one aspect, and the frequency is another aspect. So what you should do, consider as a part of material selection, you should have low density. So density should be one criteria for you. Lesser the density, higher the frequency will be. Square root of k by m, if you see the natural frequency expression. Similarly, high or low stiffness depends on whether you want to reduce the frequency or whether you want to move the frequency up. It's always not necessary that you have to increase the frequency to meet the requirements. It depends on what kind of input excitations you are dealing with. We have some examples in the later slides to explain that. Fatigue performance. So your SN curve, stress versus number of cycles, high cycle fatigue curve for fully reversed case should be good to meet the requirements. So that is one important thing. Operating temperatures. Sometimes you may have moving components like actuators, for example. You take example of tubes with the clamps mounted to the brackets. So the wear characteristics of those mating components should be tribologically met. So that is one thing which you may have to see. So material combinations and compatibility, galvanic corrosion should be avoided. So this is a general considerations. I mean, the remaining things are general considerations, but from the vibration perspective, the most important thing is fatigue performance, density, and the stiffness aspect, and the wear characteristics. Casting is another thing which you should be careful about, because fatigue performance of casted parts drastically drops. I mean, it will be almost half of the machined components most of the time. So we should be careful about manufacturing processes also when you are selecting the when you are selecting a process for arriving at your configuration at the end of the day. Okay, design may propose casting, for example. Then, as a structural analyst, I should actually come forward and say, hey, casting is going to be not a good fatigue performer, and we should be looking at some other means or machining or some other means to achieve it. Okay, something like that. So, so as the some other aspects on fatigue, surface finish factors and other modifying factors. This is general thing, so I will skip it. So all the modifying factors that generally go on general fatigue discussion should be considered adequately for vibration problem also, is what I would like to emphasize here. Okay. So now let's see what are the key elements that we should focus additionally in the design cycle against vibration. So the uncertainty part. So you have seen the damping ratios, nonlinearities, and there are many analysis assumptions that could be made as a part of the simulations itself. So without simulation, we cannot. Simulation is the first step in the overall design cycle, where we are actually trying to build confidence in the design to get it to the prototype building or to the development phase or directly to the qualification. So if you have more uncertainties, then we are away from proper predictions. So with more uncertainties, there will be high chances of failure, and there is a very low control on the risk management. Whereas when you reveal the uncertainties with more and more tests, you characterize the system or identify the system by subjecting it to early tests, then you understand the behavior of the certain features, certain material modeling. For example, you have composite materials, how you can model them either using orthotropic properties or either using equivalent Young's modulus. There are certain things which I am trying to quote as a part of this, for example. Okay. So again, the boundary conditions, how you can consider the boundary conditions. Maybe something can be considered as a bounded contact at lower excitation levels, but for higher excitation levels, they may slip. Then you may have to consider certain stiffness parameter to model that effect. So when you don't understand all these, then your predictions are subjected to a lot of uncertainty and you cannot take any decisions. So that is where we have to be focusing on in our design cycles. So if the gray items are what which you have traditionally focused when your vibration problem is severe for you. Like is analysis methods validated? Damping estimates for similar product available from legacy. So it is always important for us to understand whether either I have feature based data or product level data uh, for uh, for the damping, okay, and the boundary conditions as well. Like I said, a ball joint or a spherical joint or a kind of kinematic coupling. How do I model it uh, with at lower excitations, at higher excitations, when the preload is present, when certain friction is present? It may not be simply freely rotating, right? Sometimes there will be some stiffness associated with the because of the friction also. Okay, so we have to understand how the slip mechanism or how the kinematic coupling mechanism is working and how I can model it appropriately. So analyze with valid assumptions. Okay. Then, I mean, when you don't have the valid methods, just analyze with valid assumptions. Then, after meeting the design requirements, go for development test. If you have already sufficient confidence on the system you have pedigree from the legacy, then you go ahead and follow the existing uh, design cycle, which is quite straightforward. But when you don't have the legacy experience or the previous experience on such kind of features, then you should actually go ahead and do early development test. It's not like development test will be done after all the requirements are met in the design cycle. You should be doing a parallel development test. That is what is generally recommended. And then go ahead, validate your analysis models. Okay, that is nothing but test correlation, analysis test correlation. Then apply the updated boundary conditions, updated modeling methods, and the confidence that you built through fine tuning your analysis can be applied to optimize it further and then get to the qualification tests. So this is what the overall design cycle. In the design cycle, what additionally you should focus in parallel with developing the uh, design. Okay, there will be a number of other requirements which design will be subjected to. But when vibration is a severe case and you have uncertainties, you should definitely take up development test early. Okay, so that is one thing. So now you have seen here various factors. We have been discussing about simulations, requirements. We have been discussing about understanding the system behavior or characterizing the system. That is nothing but system identification. Then we talked about analysis to test correlation here in this design cycle. Now let's see each one in detail. What will be the contribution of each of these aspects in a successful vibration design. Okay. So now let's look at simulation considerations. So I already uh, I spoke about it sufficiently, but uh, can you guys, any one of you, just try to comment what exactly simulation considerations would be and what you think will be a role of simulation I mean simulation in the design for vibrations. Just, I mean, quickly. I don't want to be monotonous myself speaking on the topic. So I thought we'll put 1 minute over here.
with the help of simulation and considering the vibration profiles, like it may be harmonic, it may be random, we can predict the that critical zone where we can predict the failure, like the critical zone we can before testing we can locate that zone where the design need to be changed or optimized.
Exactly. Next, anyone want to add? Yeah. So, like Akash mentioned, it is definitely about understanding the efficacy of design against the uh, excitation levels, whether it is random or harmonic, whatever excitation you have. What is my response to that excitation levels, and whether it is fatigue performance is sufficient to take it to the field or the testing. Okay. But before that, we have to understand whether my simulation is rightly representing the uh, reality, or am I uh, closer to the reality. Whatever is intended is really getting predicted, because the prediction should not go so wrong, right? So that is where this section talks about what are the few aspects that we should focus to bring the simulation right in the first place. Definitely, there will be fine tuning required, like I said, during the analysis by correlating with the test data or the development test. That is another part. But before that itself, whether how I can actually make sure that I am sufficiently capturing the details in my analysis is the major thing. So few things that are quite critical here is spatial modeling. Okay, that is nothing but adequacy of the hardware considered for analysis. How mass and stiffness is captured, and while this mass and stiffness is being modeled, mass and stiffness, when I say, sometimes you can directly model a body as a simple point mass element or a lumped mass, and sometimes you can model a body as a simple stiffness. So, what are the assumptions behind those simplifications? Whether those are valid? Okay, such kind of questions we have to pose to ourselves so that we will not go grossly wrong in simulations. Even though today we have a very good computational systems of higher RAM and higher very good hardware we have for conducting these simulations, but in any case, to reduce our simulation time and to keep the models within our range of handling. So we would need definitely certain level of simplification. So that should be taken care with certain justification. Similarly, contracts and joint modeling. So like I said, the model analysis cannot handle nonlinear model as of now. So how to deal with those things? How you can still have certain joints modeled or with an equivalent linear representation for a certain nonlinearity, how you can bring it. Okay, such kind of things should be thought ahead in the modeling before modeling. Okay, then boundary conditions. Again, boundary conditions also, there will be a lot of nonlinearities that can be present. But again, within our purview of linear systems modeling, how I can equivalently model the boundary conditions is another part which we should be thinking about. Now coming to the spatial modeling, there is nothing but the mass and stiffness modeling. I think, I mean, this is my perspective of presenting the things for everyone to understand it easily. So what I generally say is we can broadly classify this spatial modeling into three groups for model simplifications, where mass alone is sufficient to model. So in first case, given a body, you model it as only mass alone, like a lumped mass or point mass. And in another case, given a body, like a spring or something, a flexible member, you can model it alone, it as a alone, I mean, as a stiffness member alone. Okay. In another case, you should be capturing it in detail with both mass and stiffness details. So how you can characterize, I mean, distribute or classify your CAD models or your actual models into this kind of thing. Let's see that. Okay. So mass alone modeling, for example, this is just an example here. So you see, this is kind of a manifold. For example, you take hydraulic manifold, which is mounted at these lugs bolted to a structure, and there are certain solenoids or certain other electronic devices or unions that are mounted towards the end. Now my area of interest is the stresses on the lugs here. So for this kind of scenario, all these solenoids as well as the unions or any electronic devices which are mounted onto the manifold, I can actually model them as a point mass because they are not having any significance with respect to their stiffness, adding behavioral change onto the mode shape of my manifold. So manifold, the way it vibrates in the uh, vertical direction, for example, here or in the lateral direction here, this is going to be only an added mass and it's not going to change the behavior because of their stiffness. So I can definitely simplify them as a point masses so that I can take advantage of a number of degrees of freedom or number of equations for solving in my FE analysis. Okay. So the next one is stiffness alone. Here, for example, you have a component which is mounted on certain flanges, for example. Okay. If, even though I'm showing it here as a big mounts, uh, what I'm trying to show is here a kind of a flange. I mean a bracket mounted on a flange, for example. So the component lugs are mounted on a boss or a flange here, and a shaft and a clamp mounted on a big mount here. So now, if this mount being a rigid one, I don't need to consider this complete mount, but the stiffness of it at the clamp may be sufficient for me to capture it. But the shaft is important for me because the component of interest here is supported by the shaft, and the shaft stiffness and the mass of shaft can influence the stresses on the component. Okay, or the response of the component itself, the mode shape of the component itself will be different when I don't consider the shaft and when I consider the shaft. So I have to be careful in considering the shaft in detail, but whereas the stiffness at the clamps and the mount can be just either fixed or can be considered as a clamping stiffness considered there. Okay. So the last one is about, you see earlier there is a big mount here, rigid one. Now I brought a flexible bracket. Now the overall response depends on uh, the bracket flexibility. Directly fix the clamp or just consider the stiffness alone, but the mass of the bracket also plays a role. I mean, how that is distributed, the stiffness distribution. I mean, you cannot just consider the stiffness element here. Along with that, the bracket frequencies and along with the shaft dynamically interacting with the bracket stiffness and bracket mass distributed will play overall role in the system frequencies. So in this case, this flexible bracket should be sufficient to capture. So these kind of questions when we pose, am I going to is my simplification or detailedly capturing something? Is it really required? For example, rigid mount here, I no need to consider the complete engine for my meshing, right? I can avoid the complete meshing of the flange and everything here because they are quite stiffer with respect to the stiffness with respect to the component comparison to the overall mount. Whereas here it is flexible. So depending upon such decisions, these three cases we have to first consider and then make out uh, whether I can represent something with only mass elements or with stiffness elements or both stiffness and mass should be captured well. That means in detail we have to mesh it. Okay. Any questions still here? Not, I will just again to appreciate what we were discussing in the previous section about the mass modeling. Another a simple example here. You have a flexible disc here. Assume that these four are the brackets, and you have a rigid body, a bigger block here, mounted on the same four brackets. Now this is modeled as a point mass, and similarly this is modeled as a point mass at the CG locations. And when the analysis was run for the full model, versus the with the point mass, and similarly for both you can see that the flexible body frequencies with the point mass is quite different from even the mode shapes. Even the mode shapes were quite different from what you would see with the actual model. Whereas when the body is quite rigid here, it's not flexible within itself. Then when you represent that with a point mass, you see that the frequencies are closely matching, even the mode shapes. So that is what a quick indication of when you should go with a point mass. Generally, people will tend to say that my area of interest is brackets, and this disk I can just model with a point mass. So that will give you a completely wrong result, and the mode shapes especially will be completely different, and you will create something which is not realistic, and you may declare that everything is passing, but whereas at the end of the day there may be some surprises when you go and test it. Yeah. So you should be careful when you are taking such decisions on these kind of modeling assumptions. Similarly, an important aspect is, I think we already discussed, touched upon this point, the adequacy of models consideration in your simulation. For example, you have some three or four components which are interacting with each other. Okay, you need not always necessary to consider all the components, uh, but whatever components that have strong interaction with your component of interest. For example, this is a manifold, for example, and I have a lot of hydraulic tubes that are going. Okay, some of these are metallic tubes with shortly clamped in a shorter distance. Some of this is a hose which is clamped somewhere here. So hose being and some of this is, for example, this is a hose, for example, and this is a harness, for example, which is clamped nearby. So harness being a flexible member, my component unit is vibrating. There will be a weak link of interaction between harness means electric harness wires. So the electric wires being flexible, it won't contribute much to the uh, dynamic interaction between these two components. So maybe I can ignore that modeling into my analysis. And similarly, when I have a metallic tube which is clamped at a shorter distance, that can influence certainly the response of my components. The mode shape itself can be different, frequency can be slightly different. Not only that, when there is a stronger mode of the component of interest, the mounting unions of the tube can undergo a severe load because the tube is resisting the movement of the component, which if you don't capture adequately, you will miss that behavior. And finally, when you only deal with your component of interest, you will find that things are fine. But when you go and test it with the all the hardware mounted, you will find that there is a surprise for you. I mean, with a failure at the mounting location. Okay, even the mode shape can be different, and you may see failure on your component of interest at the lug also. So always it should be good to understand what is the dynamic influence of the surrounding hardwares on your component is mounted on brackets. That is an important thing. If the component is not directly mounted to a boss or rigid structure, but it is mounted on brackets, you should definitely consider the effect of the bracket, because with the bracket being flexible, many times people will just say that I will consider an amplification factor for the bracket and apply a modified response onto the system. But with the bracket present, the mode shapes can be different again. So that is where we should be taking a call. So always it is suggested to perform the analysis with all these components considered, and later you simplify if you find that they are not contributing to the whole of your component of interest response. Okay, but it is good to consider them so that you will make proposals to the test plan also, so that the testing is also representative of actual reality. Okay. So again, these are some simple, some simulation considerations which I'll quickly walk through. Okay. So like the previous case, we have seen a flexible member, which you cannot model it as a point mass, but still you can consider some other methods when you want to simplify a bigger structures like this with both stiffness and mass. Model reduction techniques such as substructuring or super element analysis we call. okay, or reduced order modeling also you can call. So all these kind of techniques you can adopt and you can represent the mass which is not of your interest, but you want to capture it adequately. Okay. So now the number of degrees of freedom in your actual system here with the simplified version is very less. But you see earlier this was not matching. You have seen in a couple of slides back, this was completely off with the point mass. But when you represent it with this kind of substructure or model reduction techniques, when you utilize, you see that they exactly match. Okay. So such kind of techniques you can adopt when you want to keep your model size low and at the same time you want to capture the behavior of your surroundings adequately. Okay, some key aspects. I think we already discussed on many of this. So one important thing is you have to ensure remember that your simulation is always linear, whereas real systems are nonlinear. So the more nonlinear the real system is, you should uh, keep in your mind that whatever approximations you are making are not may not be closer to reality, and you may have to visit them when you go for test correlations. Okay, so all the modeling assumptions should be reasonable and should be justified ahead. And one important aspect I would like to emphasize in any for any simulation considerations or when you are developing standard works within your groups, that your standard work should be data driven. Means you should be for any product family. I mean, you should actually have some considerations or recommendations in your standard work for a product family wise or features wise. Like features, when I say particular joints, for example, how you should model them, whether there should be any relation with respect to the excitation levels, whether there should be any relation with respect to the stiffness versus certain forces or say stiffness versus certain excitation levels. So such kind of modeling considerations we should be developing and based on every test that you conduct on your product or certain elements in the design elements, you develop your best practices and add those to the standard work so that you will be slowly moving towards the certification by analysis or you will be having a robust analysis methods as well as the design ahead in the design cycle. I mean, when you go for development test, you will not see much gaps between your analysis to the test if you adopt that, and then you can skip that the development test route that you have to adopt for uncertainties, because this indicates that you have embraced all your uncertainties and now you are good to go with directly qualification tests instead of run. And more and more first time first pass yield or first time correlation, I mean the correlation at the first hand itself, if you achieve with your modeling methods, it is always possible for you to pass by analysis, I mean propose certification by analysis or pass by analysis for future designs or future design changes. So that is the key advantage when you maintain your data driven standard works. So that is all about the simulation considerations. Next is, I think, I mean, system identification. So this is again why we were, I mean, one element which we were discussing about in the design cycle was characterizing the non-linearities or identifying the damping present. Okay, how we can say that my simulation is right? So that needs support from the testing. Definitely, that is what we were calling it as development testing. Again, we need certain understanding or knowledge of how what kind of test to be adopted and how I can utilize testing in developing these details. So the model parameters, when we call model parameters, it is the natural frequencies, damping ratio, and the mode shapes. So those all can be established. This can be established only through test. So to understand and establish these critical parameters, we need certain tests to be conducted, and that those tests from the test data you can extract model parameters, natural frequencies, and mode shapes, and compare with your analysis. That's what when I was talking about analysis to test correlation. That is what is the whole objective all about. I mean, fine tuning your comparing your analysis results with the test data and what is the difference between my analysis natural frequencies with the test natural frequencies? how the mode shapes correlate, how the frequencies correlate. Then the damping is only a parameter from the test which will key into the analysis and see compare the responses again. So in this process, whatever assumptions which we made ahead in the analysis, all those assumptions when we revisit and update or fine tune, that is called as model updating. We'll come back to this again later in detail. So now there are various testing methods that are available depending upon the input excitations. We can see like impact hammer test, shake table test, and operational model testing, or few such testing methods which are quite common. There are several other testing methods like operational deflection shape testing and such kind of tests also. But these are the three main things which you will come across in the aviation industry. So impact hammer test definitely got a limitation with respect to the kind of energy levels that it can pump in. So the source of impact hammer test is the impulse that your impact or ping test or the ping with impact hammer when you create on the object. What is that the pulse or the shock pulse that it creates, and what is the level of energy? The frequencies that are getting excited. Okay, depending upon that, all the frequencies of your system can be observed using FFT, fast Fourier transformation in the when you post process the data. Okay, from the from the signals that you from the response that you take from these accelerometers or transducers. Okay, so it depends upon the tip of the impact hammer again, whether you choose hard tip, medium tip, or soft tip, and depending upon your frequency range of interest, you can choose the impact hammer tip. Okay, so like I said, it is easy to adopt, but the why there is a limitation is majorly because of the energy important to structure is not sufficient many times. For example, you take a tube with clamps, certain clamps, okay, loop clamp, P clamp, or block clamp, and you have strap clamps on the tungsten tubing systems. When you just go and do with impact hammer test, the energy imparted to the system will be less. Therefore, the whole the mode shape that is required to be set to exceed this kind of frictional. The clamping forces will not be possible, and therefore you will see that all the clamps are quite stiff enough or are actually giving you a bounded contact kind of scenario, fixed joints. Whereas in reality, when you subject them to a higher excitation level, such as actual engine excitation or actual shaker excitations at higher G levels, then you will see that they will have micro slippages, and therefore the frequencies will be quite different. So in such cases, impact hammer test will give you higher frequency than actual test requirement. Okay, which is a quietly a different indication. Similarly, other way is when you have nonlinearities again, like when you have contact nonlinearity, for example, when you go for you take actuator itself where you have cylinder and piston rod with a certain seals in the middle. Okay, when you go with impact hammer test for such kind of scenario, the frequencies will be shown. The frequency that you will get through the test will be very low. Okay, because the whole of the system frequency is not established because of the contact gaps. Whereas when you go for a shake table test, you will find that you will get a proper excitation levels, and that is advantage with shake table test. Okay, so like I said in the previously, this is not suitable for nonlinear systems, and more realistic scenario you can achieve by considering a shake table test. Again, for shake table test selection, you have to make many considerations to keep it high level. I am just showing you this performance curve, which you can utilize from the shaker that you are adopting. Okay, the data manuals, and based on the mass of your component and the slip table as well as the fixtures, everything you have to consider, that is the payload, and then you can identify whether your shaker is sufficient to drive the the forces that you are intending to test it to. Okay, so one key point is the fixtures should be designed stiff enough so that their natural frequency of fixture should be sufficiently away from your component of interest frequencies or unit under test frequencies. Action should not happen, and unrealistic amplification or under prediction of frequencies of your unit under test should not happen. So that is the objective here. So that is the note which I am showing here. And one more thing, still there is a limitation with the shaker, because in reality, when you see the aircraft engine, for example, the components mounted are radially on the casing and at a different locations, and then they may be interfacing with several other components, okay, in a different orientation. All of that may not be possible to accommodate within the shaker. You may try to get the actual aircraft representation or actual setup by having the fixtures. Through fixtures, you can still try to get that, but it is not always possible to achieve that. So that is where you see the actual test can be achieved only through operational model analysis or operational testing. So this is one thing where you can actually try to collect the behavior of the structure or its responses or the modes of vibration when it is undergoing undergoing actual operation with no initial excitation or non-artificial excitation. So I am not trying to excite anything through shaker or something, but I am just running the engine or operating it. Or for example, we just discussed the rotor excitation kind of thing. That is one thing. So when you measure response from such kind of systems when operated with various accelerometers on it, whatever mode shape you get can be considered as operational mode shapes. Okay, so that is actually real-time behavior, and in case of aircraft engines, you will find out something called stage-step endurance test, so which can be considered as operational model testing. Okay, so for experimental model analysis, that is through ping test, okay, or the shaker test, you need input excitation levels. Whereas for operational model analysis or deflection shapes, you don't need to have any initial input. But whereas just from the operation of the system itself, you can capture the data and find out the responses and natural frequencies of the system. Okay. So now. Uh, once the data is collected from these testing methods, our interest would be in extracting how we extract these parameters. There are lot of data acquisition systems and softwares which can help us in creating these parameters. So there will be local methods and global methods, and similarly a single method CISO and MISO, like that. Okay, multi-input, single output. So if you see here, you have single inputs and multiple inputs here. So all multiple inputs generally go under global. So global and local, when I say, it is nothing but dealing with the natural frequency in the vicinity of natural frequency and the response FRF locally to that particular point. Okay. So based on that, the parameters will be extracted. Whereas global, when we say, at a time, the whole response curve will be approximated with the curve fitting approaches, and then all the parameters will be extracted at a time for all the mode shapes, all the frequencies, and that will be reported out. So you see here, most common ones are peak picking methods, mode picking, and circle fitting methods. So these are the methods which gives us frequencies, damping. Here mode shape will not be possible because it is just the peak picking around that particular point. Whereas mode picking and circle fitting methods will give you the frequency, damping, and mode shapes as well. Okay. So similarly, you might have come across various curve fitting approaches. Okay. So such kind of approaches can be utilized to get the parameters at a global level directly. So now we have seen that, I mean, the damping ratio will be directly output from these, but how it is calculated? Either you can utilize circle fit method or line fit method or half power bandwidth method. Half power bandwidth method is quite common, which actually talks about at the 1 by root 2 times the amplitude level. The energy can be considered to be equal among the that is why we call it as half power bandwidth. The power is considered to be half there. Then when you express equations for that, it will boil down to be something like that. Okay. So using this expression, you can calculate the damping. Okay, Q is always 1 by 2 zeta amplification factor. Now the expression here is Fn by F2 minus F1. When you use this, you will get the damping. So wider this curve, I mean, if the response is much wider, that indicates that the damping is more. If it is very sharper, then it indicates that the damping is very low. So the response in your system would be therefore very high. Okay. So I think somebody was mentioning about Vivek, I think in the beginning about the nonlinearities. So especially when you deal with systems which whose responses, I mean, how to identify nonlinearities is the first question. So is it possible to identify nonlinearities by analysis? Is the first question which I would like to pose to the audience itself. 1 minute. If you are given a system with all the components detailed and everything is given to you, can you say that your system is going without any prior experience? Can you say that your system is going to be nonlinear, or what level of nonlinearity will be present in your system? Anyone? Answer is no. Analysis cannot predict anything before. Analysis rather needs input from the test to predict the nonlinear behavior later for you. Okay. You can only model the nonlinear behavior in your analysis by the inputs from the test. Okay. So the test is the one thing which we'll talk about the nonlinearities present in the system. So when you test something for a varying inputs, okay, the frequency you can see here with increasing excitation, your frequency, natural frequency of the system is keep varying, increasing, okay, or it can reduce with the increase in the excitation levels. Maybe the system can become softened when you have more excitation, like I mentioned about the tube and the clamping scenario, where with the higher excitation levels, the clamping force can be exceeded and your tube can slip through the clamps and therefore the frequency drops. So that is a kind of a nonlinearity. Similarly, you take actuators with clearance joints. I mean, piston will have a clearance, piston head will have clearance with the cylinder, right? So those when the piston rod or at these joints the clearance should close, and during that process you will have stiffness being built with the excitation levels that will result in certain nonlinear stiffness relation. Okay, so when you are restoring force versus displacement is not linear, but whether if there is a kind of nonlinearity resulting in higher restoring force with the displacement or lesser restoring force with the displacement, that can be termed as softening or hardening. So generally, this kind of polynomial hardening or contact stiffness, contact nonlinearity, or kind of uh, change. I mean, change in the boundary conditions, a step change in the boundary conditions. Like suddenly there can be a contact after a certain deflection, for example. So all these scenarios are nonlinear behaviors. So how do we establish that? You have to test sufficiently with increasing level of excitations. Okay, from 1G till 10G, for example, you at various steps you sweep your system, then you plot them and understand if the frequencies are quite different, then it is a nonlinear behavior. And this behavior can now be characterized by achieving a curve fitting again between these. The natural frequency as a function of the stiffness. You can bring that stiffness as either cubic nonlinearity or a polynomial nonlinearity in your equation of motion, and then you can try to solve that equation of motion to get the overall response. So when you see such kind of behavior, either I mean, this is called jump phenomenon. So the actual frequency, when you update your equation of motion and try to solve that, it should actually follow the backbone curve like this. But whereas in reality, what happens is you have already reached the higher frequency here. I mean, response at a higher frequency, and you cannot trace back. So in the upsweep means here the shake table test when you are sweeping from lower frequency to higher frequency. This is how the curve is tracing. Okay. And once it reaches here, it will just suddenly drops, because mathematically, even though it shows the response should be like this, as the frequency has already surpassed, it will just drops down like that. That is why this kind of phenomena is called gem phenomena, and this can be observed in all kind of cubic nonlinearities or polynomial stiffness nonlinearities or clearance nonlinearities. So when you are down sweeping them, okay, you will find a different frequency and different response level. All that is because it is tracing back this curve here. It cannot go back to the previous frequency when it is uh, coming down. So what I am trying to conclude here is, one test is you have to test for varying excitation levels, and another one is you have to test for uh, upsweep and downsweep to understand the kind of nonlinearity is present. So when you do all these exercises, you will understand that there is a nonlinearity present, but what is that influence of that is important to us. Is it really significant? Is it really uh, so heavy nonlinearity that I should worry about in my design and analysis? Is one thing which we should focus on. If it is not, then definitely you can make linear assumptions and go ahead. So in these kind of situations, already like I pointed out, you can always come up with a regression analysis, and you can develop equation. You can develop a transfer function between your natural frequency and or the stiffness, additional stiffness that you want to model as a function of excitation levels. Okay, so that as the excitation level change, your the between the two components that are interfacing, you can model the stiffness as a function of the excitation frequency, so that you can always predict the behavior well in ahead. So that is where I'm trying to say that the data driven standard works. If you for you if in your product family, if this kind of nonlinearity is quite critical, you characterize it through the system identification by conducting sufficient tests, establish transfer functions to linearize that nonlinearity, and conquer that within your linear world of model analysis by having adequate behavior captured uh, with I mean this kind of assumptions. Okay. Any questions here? So that is all about the testing part. So the next significant element that we were discussing in the design cycle when we were about the additional items to focus is model updating or analysis validation. So this also plays a very crucial role in your design for vibration, because like I said, you always started with your analysis assumptions. If you have adequate background on the particular product family, then you are fine. You don't need to worry much. But when you are dealing with something very new, a new material or a new configuration or a new features or a new, uh, uh, I mean, something which you are researching about, which you are not aware in the past, then you should be doing tests and update your model. That is all about model updating. Okay. So analytically, how you are starting, you are building your spatial model. You have model, which is nothing but your natural frequencies, eigenvectors, and whereas the damping is an input from your known understanding, and then you are constructing response models, FRFs. Whereas the experimental analysis, if you see, it is actually starting with measurements, that is nothing but response model, and from that you can create model, that is nothing but the extraction of data acquisition system. I have shown earlier how you can extract the parameters, and we rarely go till spatial model, evolving to spatial model based on experimental results. So we always stop it here. So why I am showing this is to give us a clue at what data we can utilize from the test to compare with our analysis. So at the two stages, you can utilize the data. One is model-based correlation methods. You can do model analysis on the experimental data, extract natural frequencies, eigenvectors. Damping is only required for response. You keep that aside. First, we are interested in natural frequencies and eigenvectors. So get that from the experimental data. You have them from the analytical data and compare them. Okay. And the next method is response-based correlation methods. So we have frequency response methods also, frequency domain methods, but most common one is model based approaches. So we'll focus in the next slide how we can deal with analysis correlation or build confidence in your analytical models based on model based correlation methods. So anybody heard about MAC, COMAC and AutoMAC? Here. Are you guys with me?
Yes, sir.
Yeah, yeah. Just trying to make sure that nobody's sleeping in the afternoon.
Got.
Yeah. So MAC is nothing but model adherence criteria. As you see from the model domain, model itself talks about the model domain. So what we are trying to do here is based on the least square approach, we are trying to bring correlation between the analytical mode shapes and the experiment. X stands for experiment, A stands for analytical. Okay. So we are trying to get eigenvectors from the experiment and the analysis, and then get based on this expression, which is actually dealing with least square approach, and you get the correlation matrix between the analysis modes and the test modes. So whatever mode, I mean the MAC number, which is more than zero point 0.8 or zero point 0.9, we can always consider them to be well correlated. Okay. And which are off or not correlated well. For example, here 0.56, for instance, or 0.38. We can say that these modes are not well correlated. And you can also observe that there is a multiple correlation it can show. Like for example, this fifth mode from analysis, say, is showing bit correlation with fifth mode from the test and sixth mode from the test also. Okay, so those two modes may be bit similar, or the analysis is not adequately captured at this mode. But is it really required to worry about all the modes? May not be. Our major focus will be on the first few critical modes, majorly the fundamental modes, and whatever modes are severe from the analysis will all and whatever modes were dwelled in the testing. Okay, with those responses, because these are coming from the testing and we might have dwelled them or we may have just swept them. And from the sweep data, if the response is significantly high for certain modes, all those modes should correlate in the analysis is our target. So that we can, before going for dwelling, we can actually, predict whether the system is going to fail or pass, and then we can take a call on moving ahead with the testing. So that is all about model adherence criteria. So what is COMAC? COMAC is coordinate model adherence criteria. So the MAC, what it does is it takes the eigenvector. That means, for example, you have 5 accelerometers on the beam. To all these 5 accelerometers, what is the mode shape from these responses in each direction? What is how if it constructs the response, you get the mode shape. So that mode shape is compared for MAC, whereas here at each accelerometer, that means at each coordinate, when we say it is a degrees of freedom, at each coordinate or at each degree of freedom, it will try to figure out what is the correlation. So MAC is going to give us a model correlation, mode shape correlation, whereas COMAC is going to give you correlation at each degrees of freedom, means at each accelerometer location. What is the level of correlation? So why this COMAC is required, we'll see in the next slides. Okay. AutoMAC. AutoMAC is auto here when we say it's a self, right? The meaning of auto is self. So AutoMAC is nothing but the model adherence criteria with the self data. Okay, with itself, I mean. Okay. So this will help you to actually decide on the number of accelerometers and the location of accelerometers that you would like to have in the testing. So before going for the testing, if you conduct AutoMAC by considering the responses from your model itself, assuming that these are the critical mode shapes, and from these critical mode shapes, these are the accelerometer locations which I would like to have, and that AutoMAC, if it is giving you a good result on predicting all the correlation matrix that you intend to be perfect, then that actually gives you exact locations or good locations of the accelerometers. Okay, so we'll see the physical significance of it in the next slide. Automac. So if you see the automac major leads required for adequacy of accelerometers, I have taken a simple beam here with one accelerometer. Now this is the full analysis, and this is from point one. I mean from this point one analysis. So I am assuming that this is the from the analysis itself. I am extracting the data at one point, and I am considering that to be a test data. Okay. Now when I go ahead and compare all the first four modes here against the test data, I mean this is, for example, you consider it to be a test data. From the analysis, when I compare with this, you see that all the modes are correlating, and there is a cross correlation also. This indicates that even the fourth mode correlates with the first mode of the test. Okay, first mode correlates with the fourth mode of the test, which is wrong. I mean that is not the reality, right? Because you have only one accelerometer, that is not giving you enough clue that these are not the modes that are correlating. Okay, even though you have frequency to distinguish, but that is not the way we should be working. Sometimes you may have close modes. Now you see that first mode correlates with this, and second mode correlates with the first mode, and first mode slightly correlates with the second mode. To avoid these situations, now I have two accelerometers, for example. Even then, I see that fourth mode is shown to be correlating with the first mode. So this indicates that the accelerometers are not still adequate for me to consider in the testing. So now I am going with three accelerometers. You see the perfect match only on the diagonal side. So this is indicating me that these are the three accelerometers that I need in the testing to pick these four modes adequately, so that I can utilize them in the validation stage for my analysis. That is what the advantage of Automac. Okay. So now if you see the overall summary of model-based correlation technique, you have analytical model which you used for the analysis, then you used Automac to identify the accelerometers, you went ahead and tested and extracted the model parameters, and from the analytical model, you got the eigenvectors, now you calculated the MAC, that is model agents criterion. Now, if all critical modes are correlating well, when I say correlating well, mode shape should be having a MAC of 0.9 or 0.8 at least. Okay, and the frequency should be within plus or minus 10%. It is because of the analysis assumptions, and the models may have we may be considering mean models in analysis, but based on the tolerances, you may have different kind of dimensions in the actual test. So to cater all these and the kind of assumptions we make, 10% variation on natural frequencies is expected. So that is allowed. So when you have natural frequencies within 10% variation and the mode shape with a MAC greater than 0.9, that can be treated as very good, and you can consider that your model is validated well. If not, you can take up COMAC, understanding which accelerometers locations have deviated, or you can actually have graphical interpolations of this response data and make out some observations or inferences from that and try to incorporate for the model updating. And model updating again is all about revisiting analysis assumptions. You may have frequency difference greater than 10% here. Then whether you have modeled something over stiffening is happening is in your system, or something is not adequately captured under stiffness, or stiffness is not adequately captured. There may be several questions that can be answered when you revisit your assumptions based on the test data. Without test data, all that is the assumption. Now you have test data to back up your fine tuning the boundary conditions. So all that things you do here, and then again calculate the MAC and the frequency correlation part, and you have to do these iterations until you get the mode shape match. Without mode shape matching, the analysis is useless, because without the mode shape correct with whatever excitation levels you apply and response you calculate, your critical location is not predicted well. Okay, so the mode shape is the critical point here to be captured. Okay, so that is all about the correlation part or the analysis validation, which is a quite important step. Now the last module in this section, which we reached, I think another 15 minutes I will take as a part of this. Okay, maybe slightly 5 minutes over spilling. Is all about vibration mitigation and control. See, this this mechanical system can be grouped into three different sections. One is a vibration excitation, mechanical system design itself, and vibration response. So all these things contribute towards the vibration response. All the things like excitation levels contributes, system design, what is the damping overall, and overall vibration response that is it is resulted to. So in order for us to reduce the vibration response, that is mitigating the vibration, either you can go for isolation or design modifications or control, that means observing the vibration. So let's see all these three different aspects how we can deal with. So now earlier whatever we discussed was all about simulation part, the testing part, what are the contribution of those elements. Now we are seeing the design aspects of how to deal with the vibration, which I think Akash asked a question how we can limit the responses, right? So that will be answered here. To mitigate vibration by design, isolate or control. Okay. So these are the three parameters. Now, if you look at vibration isolation, so you can design the vibration isolation. When I say the word itself talks about keeping my system natural frequencies away from the operating range. Okay. So for example, here, this is the operating range. Okay, from here to here. Now, if I design such a way that there is no natural frequency in this operating range, then that is called as vibration isolation. So where it is possible, especially for the components such as blocks, manifolds, or electronic systems, which we anticipate that the vibration should not disturb the activity functionality of the electronic boxes, especially FADEC, and you have a lot of control systems on the engines. FADEC is full authority digital engine control. Okay, so such kind of systems, electronic aircraft electronic controls, AECs on the wings, and you will have several such control systems that needs to be isolated from the excitations. So that is one key requirement over there. That is why you see that we can design the vibration isolation systems, and the whole purpose is to keep the natural frequency of the system away from the operating range. So how you do it? If you see the base excitation problem here, you have seen that this is the point where the response becomes 1, okay, which actually comes at 1 by root 2 times, sorry, root 2 times the natural frequency. So the excitation frequency, when it is root 2 times the natural frequency of the system, you see that the amplification factor is 1. Okay. So to take this advantage of this kind of behavior, what we do is we design the spring soft mount we call. So these springs, mounting springs, are the elastomeric mounts for softness, or you take viscoelastic materials as damping elements again along with the vibration isolation background. Okay, so you design it such a way that you have your natural frequency at 1 by root 2 times this point. So if you say this is your operating range, okay, this is your operating range, then you keep your natural frequency of the system along with the soft mounts. Okay, that means this is going to be a rigid body and you are having a spring here. So with that frequency, isolated natural frequency at 1 by root 2 times, 1 by root 2 times the operating range, then you can say that your amplification is never going to be more than 1. Okay. So that is, you can anticipate, you can appreciate that when you see this example here. So this is a simple beam. Okay. When you see it is stiffly mounted in the ends, the frequency is 597.7 hertz. Okay. And you can see a deflection mode shape. So that is not anticipated. I don't want such kind of behavior on this system. I assume that it is an electronic controller, okay, system. So now what I did, I have mounted springs on the ends, soft mounted. Then you see that only rigid body mode will exist, and that will be towards the below the operating range. So when you are operating the system, this will actually pass in the transition itself, and when the system reaches, the overall system reaches operating, it will be in this zone, whereas we don't have any frequency in that zone. So we are safe. So that is the fundamental behind the isolation system, vibration isolation. And one thing we should be careful all about is the stiffness of the mount also. So for example, our component is mounted on brackets, then as a flexible system with a hard mount. Okay, I mean here, what I mean say is you have to be careful with the flexibility of the component here. So if the component itself is flexible, here it is a stiffer one. Here it is a flexible one. You see the frequency differences 59.7 and 597.7 hertz. So when you have to sufficiently define the softer spring so that you will not end up in this kind of relative deflections. So the flexibility of the system should also be accounted when you are defining the spring, designing the spring when you are dealing with a flexible system to be isolated. Okay. System design is the second module, which we'll see now. So system design, when I talk about it, is nothing but the configuration that we are coming up with, the shape, thickness, size, everything for the requirements. So now, how I can deal with it? What additionally I can look into when I deal with the different excitations. So what I can do is, depending upon the exact kind of excitation, for example, I have harmonic excitation here, okay, or the random excitation, depending upon that and the kind of, if your natural frequency falls at 1, for example, here, if my natural frequency is somewhere here, then, and it is failing, I mean, this is for Akash questions earlier. If my natural frequency is here and it is now the response is so high that I am unable to pass the requirements, now I see that there is a sudden change in the uh, excitation levels at towards the left. Okay, so this indicates that if I reduce my natural frequency of the system by any means, okay, that will actually help me in reducing the uh, excitation levels, and then thereby the system be response and it will meet the requirements. This is some example which I am trying to quote. You have all the 3 points, so don't worry about this unrealistic example, hypothetical one. But you have now second case where acceleration is constant again here. Okay, and there is a huge range. I mean, I cannot go and reduce to uh, reduce frequency so much that I can enter into somewhere here. And you have to be careful that it is a harmonic excitation. So acceleration is equal to omega square x. Okay. So omega square x, when I am saying here, always in case of vibration, we have to see the responses in terms of displacement. So x is nothing but acceleration by omega square. Okay. So as acceleration reduces, your input excitation is in fact increasing. Okay. And if it is moving towards, I mean, when you are increasing the frequency, your input excitation in terms of displacement is reducing. So in such cases where you have constant amplitude, I mean constant acceleration as the input, okay, you should try to increase your frequency. Like a natural frequency increase can help in reducing the responses by reducing your input excitation in terms of X levels, displacements. Whereas when you, this is nothing but constant amplitude. When I'm saying constant amplitude, displacement constant, double amplitude constant here. Okay, when you consider, when you have such kind of scenario, you can actually reduce the frequency, because at any point here on this, assuming single degree of freedom behavior, you will have the same output. Input is same, displacement input is same. With the 2 zeta you apply on that, your output will be same, whatever you maintain the natural frequency. So in such cases, if you reduce the stiffness of the system, you know the displacement driven problems, right? When you apply force, you need higher stiffness. When you apply displacement, you have to reduce the stiffness to have lesser forces resultant in the system. So you reduce the stiffness so that with the reduction in the frequency, the objective is not reducing the frequency here, but with the reduction in the stiffness for the same double amplitude input, your stresses will be less. We'll see that some examples. Then similarly, random excitation, if you see, you may be knowing that Smil's equation is one thing which we use for equivalent static analysis, which can be again converted with this expression. From these expressions itself, you can make out that the product of Fn and acceleration spectral density input, this should be minimized, or Fn increase. I mean, when you increase the natural frequency, definitely the YRMS, I mean response in terms of displacements, root mean square value is going to be reduced. So playing with this minimization of these parameters will help you to naturally reduce your stress levels. Okay, so that is the key thing. Now let's see some of these harmonic related assumptions that I quoted with some examples. Before that, I think let's see what else we can do. So before going for any gross level design changes when your system fails, always try to optimize the stress concentration regions and explore local design changes, because you don't need to always modify everything, because when you modify the whole section along with the stiffness, your mass is also going to change again, and you may end up in lot of iterations. Before that, you always see whether you have optimized your stress concentrations and bring local design changes for the bending, because most of the time vibration is nothing but bending stresses. So locally you try to tweak the design to meet the requirements. Okay. So now a few examples about that harmonic thing, whatever I mentioned earlier. Now stiffness change as per input excitation. So like in this particular case, what I was saying, like a constant acceleration requirement, when you increase the stiffness so that uh, your response input excitation itself will reduce. Okay. So one such example you can see here, a cantilever beam with circular cross section is considered a hollow one. So you have diameter and thickness and sorry, I mean this is a generic statement, like diameter, thickness, width, etc. and mass and stiffness of the beams can be understood. And in this particular problem, it is a hollow section. You can see frequency versus diameter for constant thickness. It increases with increase in diameter, and second. And the response, you can see this is actually response, total deformation. Okay, the total deformation reduces with for constant dia. Okay, so with this, actually, what I'm trying to indicate is that your output response actually reduces with uh, increase in the frequency. Okay, so when you have constant acceleration input, increase in frequency will help. And this is the another example which where we are talking about the constant displacement, that is constant amplitude. Okay, so in this particular case, the takeaway was about maintaining, reducing the stiffness. So now you see, I think I was mixing up. One second. Yeah, sorry, I think I was mixing up. This is just about the previous example itself. I try to change the stiffness of the component and increase the stiffness here. Okay, so the frequency, yeah. So E by rho ratio, correct. Here I think, sorry, there was some mix up here. So what I was trying to do is stiffness change as per input excitation, but beware of E by rho ratio of materials. So this is the point which I was trying to emphasize here. Young's modulus to stiffness ratio. Most often what we think is that to make it stiff, I will just only concentrate on the E value. So I will just change the material from aluminum to steel. Okay. So for example, you see here, I am just changing the material from aluminum to steel. Okay. Got it right? For the constant E by rho ratio. So when I just change the E value, then I maintain the constant E by rho ratio, because the density to Young's modulus ratio for aluminum and steel will be more or less same. So the frequencies will remain same, but for the stiffer one, you see that the deflections also are going to be same, because the frequencies and input excitations are same. But as the stiffer one is undergoing the same deflection, you are seeing higher stresses. Okay, so we should be careful about just not talking about changing the material from aluminum to steel will help you completely, but the stresses are also equally increasing. Okay, or also we should be mindful about that. But what advantage you will have when you change from aluminum to steel in certain cases is the fatigue properties. Fatigue properties of steel would be quite severe or superior compared to the aluminum, whereas aluminum may also need certain surface treatments, certain anodization for to avoid corrosion protection against corrosion. So all that will actually make aluminum so inferior with respect to the fatigue performance. So that way it may be helpful, but we cannot just say that changing from aluminum to steel will certainly help me every time. That was the, I mean, sorry for the confusion here. I just inserted this part here. So that was the thing which I was trying to bring. Similarly, the next one, stiffness change as per input excitation, again the same point. For the same materials, for example, here, now reducing the constant amplitude input. This is what I was saying. This is about the first point, third point, which I am talking about, constant amplitude input. Now you see, I am just reducing the stiffness of the system. So what I did here, I reduced the frequency in such case by reducing the cross section thickness of this member. Okay. So with that, what happened? You can see the deflection remains more or less same because this is the constant amplitude input. But whereas the stress has come down significantly compared to the earlier one, and that is because the stiffness of the system has come down. And for the reduced stiffness, for the same deflection, you will see a lesser stresses. So with these guidelines, when you keep in your mind, you can always try to manipulate or the change the design suggestions you can make so that you can be closer to meeting the requirements. So what key takeaway from this slide is that it's always not necessary to stiffen the system. I mean, most of the times what people do is add material to the system or the components so that they meet the requirements, but it's not necessary. Sometimes you can keep it flexible. You can make it more flexible to meet against the vibration requirements when you have a constant W amplitude as the requirement. Okay. Similarly, stiffness change can be achieved with this kind of simple design changes. You can have ribs locally. When I say local design changes, you no need to have thickened sheets, but you have to look for how you can achieve the frequency drive by having this kind of ribs or gussets. That is one thing. And your mass center of gravity of this kind of overhang systems should be always closer to the mounts. So for the electronic systems also, if you can mount something packaging of electronic systems, if you can mount something close to the fixity, something like that, CG, if you maintain, that is more better than having something like this. Similarly, some more considerations. You can always look for coupling and decoupling of modes of the system vibrations. Sometimes coupling your modes with the adjacent system modes can be beneficial. Sometimes decoupling the modes within your system can be beneficial. When I say decoupling and coupling, it is a physical way of coupling the modes. For example, you take a duct here and a flexible smaller tube, and the smaller tube, when it is having more unsupported length, you can actually connect it to a duct adjacent to it so that it is getting enough support. So that is one way of looking at the design solutions. Whereas when the flexible tube is actually having a fixity nearby and you support it nearby, then under the mode shapes of this duct, there will be a chances that it will fail at the fixity. So this is not recommended. So you can always look for this kind of solutions, like how I can dynamically decouple or couple the systems for desired response. So I think this is my few more slides are there. Then you can explore the latest analysis tools that you have. For example, topology optimization. This is for some fixture. I am just trying to show some random example. You can try to get the best layout of mass and stiffness distribution for your designs and utilize it for optimized versions as well as for the frequency that you intended to have. So topology optimization as well as the parametric optimization should help you in getting the desired frequency. So structural dynamic modifications based on these sensitivities you should adopt if it is really important for you in achieving certain frequencies and responses. The last one is about the damping. Till now, whatever we discussed was the two parts, that is the isolation part, isolating from the input excitation itself, and the second one was system design. how to deal with the system design when it is inevitable and when your system is undergoing those excitation levels and resonance is going to occur. So now we'll see how to deal with absorbing the vibrations. So the damping is one important part. We already discussed in the beginning that there are various sources that will contribute to the overall damping in the system. For example, hysteretic and viscoelastic. Similarly, structural damping because of column friction and the joints and interfaces, and the hysteresis itself is a structural damping, which can be again internal damping also you can say. And other elements such as the fluid structure interaction. If you have a fluid sloshing in a tank or the fluid tank, for example, fuel tank, for example, so that may also contribute to certain damping. Or the half-filled pipes or the full-filled pipes, they may respond differently. So all these are different ways you will get damping in your system and depends on the mode shape again. So these are some from the literature. If you see, these are some indication of material damping alone that is present. So why I brought this is to make you understand that material wise, I mean the hysteresis damping that you see is hardly present in the, I mean it is not a major contributor at all. You see here, this is varying from 0.2 percentage to 1%, 0.1 percentage, okay, or 1 percentage. Okay, similarly, aluminum, if you see, it is even lesser. Okay, 0.2 to 1 percentage is for steel, and for aluminum, it is even lesser. So, all this is indicating that the damping that you get most out of your system is because of other elements, not because of the internal damping. Okay, the material damping alone is not a contributor, but the damping that you get is the structural damping at joints and interfaces and so on. So now when my system is designed and when I have certain damping characteristics already established and I cannot redesign my system or the second element, whatever we are discussing about system design, everything is matured and I want to, my system is still failing. So another alternative is looking at how I incorporate damping into my system. Okay. So that is called as induced damping. Okay. So damping treatments. Additive damping treatments is what we can call such a kind of exercise. So there are, this is taken from Harris Shock and Vibration Handbook. Okay. I have references in the end. So when you take up additive damping treatments, there are various methods. Few of popular ones are viscoelastic material treatments. So this free layer damping and constrained layer damping are viscoelastic material based damping treatments. And then you have integral damping treatments, which can come from the kind of construction itself. And then the tune dampers are vibration absorbers. You see the damping mechanism contribution from various sources. Constrained layer damping actually gives higher damping among all. Okay, so that is a topic of interest for many to adopt this kind of additive damping treatments. So what exactly it is, if you see. So this is your base structure. Okay, for example, you take this engine case. Okay, some automotive engine case, crankcase. Then you have this is the viscoelastic material that is attached here. This is a constrained layer damper here. So this was actually having undergoing very high vibrations or the responses under when subjected to vibration environment. Okay, it is a baseline. When you have that viscoelastic material identified based on the natural frequencies and the nomograms of the material established, okay, then you see that the response is completely dissipated. Okay, the basic phenomena behind it is the shear deformations of this viscoelastic material that actually happens between the constrained layer, which is again a metallic layer on the top of it, okay, and the base structure. So when the structure is undergoing bend shape or the mode shape, your viscoelastic material actually tends to have shear deformations, which results in this energy dissipation through the shear deformations. So heat is getting liberated or generated through this, and the energy gets dissipated. So that is how you see that the whole of response is suppressed. Okay, so this kind of things can be adopted, and they are now widely utilized in aerospace industries as well. And when you don't consider this constrained layer, that will be called as free layer damping. It may not be so superior as constrained layer damping, but that works on flexural deflections principle instead of shear deformations principle. And the last one is about the vibration observer. So I think many of you might have seen this heavy, high-rised buildings or the big hotels in Dubai. I think there will be a suspended mass in the center of the building on the top. Okay, all that is actually counteracting the vibrations that the building is undergoing primarily. So the basic principle is nothing but instead of having a single critical mode of the mass one, okay, that is our primary mass component of interest. You design additional secondary mass which actually splits this. I mean, this is like this acts in the opposing direction to this as an inertia, and then because overall this is becoming a 2 degrees of freedom model now, and now there will be two different modes instead of one single mode, and the design criteria is having these two frequency, the ratio of the second frequency to the first frequency as 1. Now, for example, you choose mass ratio as 0.2, for example, then you will have two modes at 0.8 and 1.25 or around like that. Okay, so this will be at 0.8 and 1.25. You will have two frequencies, and the mass of the M1 here green color. I think the colors were not matching here. Taken from some internet source. So this primary mass response will drastically come down because of the inertial load contracting from the mass 2. Okay, so the secondary mass will have bit higher responses than the primary mass, but the primary mass is will be surviving the kind of response excitations that we have. Okay, so with this kind of approaches, we can mitigate the vibration environment and various other factors that we discussed in the beginning. With all that, I will conclude this presentation with a simple statement saying that successful design against vibration is possible when you deal with system design properly, that is configuration, method, and process. You have right analysis assumptions which are getting fine-tuned with lot of development tests, and the damping and analysis assumptions, like I said, are are kept improved, and you have data-driven standard works. You have legacy data to begin with, supporting your damping and analysis assumptions. Similarly, damping ratio getting updated from the tests, and you have materials knowledge. You have good, knowledge on the materials, and understand the fatigue performance of the materials that you choose. Okay, and the vibration control aspects that we discussed, the three different ways of mitigating the vibration, that is isolation or system design itself, or the vibration absorption by inducing damping to the system. So with all these options and with all these explored well, and having thorough understanding on all these great aspects will make us to uh, have a robust solution against the vibration problems. And not only that, the key takeaway here is it's an integrated approach. Vibration design for vibration is an integrated approach. You have to work with the design, you have to work with the systems team, you have to work with the materials team, you have to work with testing team. So it's a simulation. I mean, it's like structures, design, testing, materials all together. When they work together, they will have a very good and quick solution for vibration problems. So that's the last slide, and these are the references which you can refer to, and definitely the second one here is a very good book, DJ Evans, Model Testing Theory, Practice and Application. You will get lot of information on learning nonlinear vibrations as well through this book, how to identify nonlinearities and all this stuff. And anyway, for fundamentals, theory of vibrations with applications, Thompson is a very good book. And if you get chance, download this Harris Shock and Vibration Handbook. You'll get ready references for many things. And the vibration control part, whatever I spoke, most of them is from this book, Clarence de Silva. Okay. Thank you. Any questions overall?
Yes, Pawan.
Yeah.
That was a nice presentation, Pawan. Thank you.
I think Jay Kumar has raised his hand. Jay Kumar, you have any question over there?
Hello, Pawan.
Yeah,
That was a nice presentation. Thank you.
thanks, Ajit.
I have one question. Uh, we have to take displacement frequency plot or velocity frequency plot or acceleration frequency plot.
Yeah, that is a nice question. It depends on, it depends on the kind of, you can take acceleration frequency plot most of the times because at higher frequencies, your displacement may not be so great to appreciate. Okay. So that is the reason most of the times we will take acceleration FRFs, accelerants. But
Okay.
but one criteria is like if you want to understand whether the damping present in your system is viscous or structural damping, you can try to plot a Nyquist plot with mobility. If the mobility is a proper circle in the Nyquist plot, mobility response is around the natural frequency is a proper circle in circle fit. If you get in the Nyquist plot, then it is a viscous damping that you have predominantly. Whereas if receptance you get as a receptance means displacement response, if that you get as a proper circle in Nyquist plot, then it is the structural damping that you have majorly.
Okay.
You can get lot of this information in DJ Evans textbook to run through.
Okay, fine.
Yeah. I didn't
Thank
cover that, but that is I thought of covering that with interest of time. I didn't keep that in my presentation, but otherwise I definitely wanted to keep that somewhere in the Nyquist plot circle fit, right? There I
Okay.
wanted to fit that. So that yeah, no problem.
Yeah.
Any other questions?
No, and one more thing is that, as you said, the frequency, if the frequency is higher, we'll be taking acceleration in consideration for acceleration and frequency plot. So how we will correlate with the graphs? So could you please tell me in very short way?
During FRFs correlation,
Yeah.
you are saying, right? Okay.
Yes.
See, generally, before going for FRFs correlation, FRFs means that is response correlation methods. Okay. So you have frequency response adherence criterion, frequency domain adherence criterion. There are two different methods like that, but that is very not so evolved currently to utilize with the softwares or otherwise we have to develop our own codes to utilize. So, however, we can always do harmonic sweep in our analysis, or if it is random vibration analysis, we can take spectral density plots out of our responses analysis and we can overlay on the test plot. Okay.
Okay.
Got it right. And then that
Yeah.
can actually give us, but that is again a cumbersome process because you have to take all the direction plots and even sometimes the cross axis responses also we have to see. It's not necessary that always in axis will be predominant. So for the mode shape to be commented, okay, whether the mode shape is properly matching or not, all the three directions, all the accelerometers, everything should be properly overlaid, and then you can make a comment about mode shape match. Okay.
Okay.
So to
Thank you.
avoid all that, it's best to come to model adherence criterion or the model analysis wise, and then just check the mode shapes based on that. Okay.
Okay. Thank you. Thank you so much, Pawan.
Thank you.
I think Jay Kumar, you have any questions? I think there is one question from Sridhar in the chat, like how to reduce peak resonance while doing vibration test. I think you answered it, but
Why?
if you want to take
Yeah. While doing the vibration test, we cannot reduce the peak. Okay. You can only do that by reducing your excitation levels. But if the excitation levels is the customer requirement or it's coming from certain source which you have to honor, then you cannot do anything at the test stage. You have to come back, understand the system design again, and incorporate these kind of damping methods, additive damping treatments, or change your design itself to meet that. If it is so high during the sleep. Does that answer your question, Sridhar? Because test is the verification stage where we cannot manipulate anything. We have to just capture the responses.
I think
Yes.
that's what we have. Pawan,
Yeah.
thank you for the presentation. Ilango, should we take a 5 minutes break, a bio break, and then we'll start with
Sure,
Jitendra?
sure.
Is it okay with all of you, Jitendra?
Yes, I'm okay. Thanks, Sandeep. Yep. We
Yeah.
can
Thank
have
you.
5 minutes break.
Yeah. What we will do is we'll come back at 4:32. I think we also need to finish up the session, so I request you all to come back in 5 minutes. I will start.
Thanks, Sandeep. Thanks, everyone. Thanks,
Thank you.
everyone, for giving me this opportunity. I hope I will continue many sessions in future. This is my first
Yes,
session
yes,
for PDP. Thank you.
yes. Thank you.
Give our practices and their benefits in design and development. So, before starting, I just wanted to understand I believe everyone would have heard this terminology called MRO, right? Yeah, just maybe show of hand or just yes. Yep. Okay. Yeah. So basically, we know that MRO is nothing but maintenance, repair, and overhaul. So this terminology is basically used for, maintaining, repairing, and overhauling the aircrafts which are in service. Basically, all the operators, all the airlines, they are doing the, getting their aircrafts maintained, repaired, and overhauled throughout the life cycle of the aircraft for ensuring the availability and airworthiness of the aircraft, right? So, um, how the MRO practices or how the business of MRO basically, is done, and how it can help as a design engineer, means we as a design engineer think about, like, okay, like we will design and develop our products or systems or aircraft, and then somebody will use it, then for upkeepment of a aircraft somebody will do the maintenance, and that's it, right? Means we are not bothered to be linked with the MROs directly. But when as a reliability and safety professional for last 12 years, and before that as a design engineer for 2 years initially, I got a chance to look at some of the things which are happening in the MRO businesses, and how that is beneficial for a design engineer. That's what I'm going to cover today. So yeah, the agenda would be like introduction to the MRO. What are the regulations that MRO services are driven by? How a typical MRO process flow happens? What is the importance of MRO for design and development? Again, basically, just to re-emphasize the same point, help in engineering that MROs practices can provide. Benefits to businesses, basically running the organizations which are doing the engineering, and then a little bit of a glimpses of a current MRO technologies and the futures, and then challenges as well. Means when we have a benefit, so we also want to see the challenges as well, right? So as I said, like maintenance, repair, and overhaul, that is the expanded form of MRO. So it's a that business where we are just talking about ensuring that aircrafts are always at their fullest availability. Okay, basically, if you think about cost of cancellation or delays for the aircraft, it's a very big cost. So that's why MRO businesses are very important. The other point which I want to make sure that we understand the importance of MRO is like what happens is there will be one big OEM like Airbus or Boeing. They will be making the aircraft. For making those aircraft, they will acquire some systems. For those systems, they will go to the suppliers who are providing system level solutions to the OEMs. Then aircraft is sold to the airlines who are basically operating those aircrafts. Now what happens is that when we start looking at MRO facility or MRO practices only from a aftermarket business kind of thing, we sometimes forget that it can be a very useful tool for engineering analysis as well. And basically what happens is now, so within that segment, I just wanted to introduce this terminology called repair stations. So repair stations are those stations which are allowed to do the maintenance, repair, and overhauling of the aircrafts. Okay. Now, everyone must be knowing that aerospace industry is a very regulated industry. So anyone cannot do the MRO, activities. So somebody has to get a license. Just like when OEMs make the aircraft, they get the certification from the civil certification authorities, and then only they can sell those aircraft. Similarly, MROs also means MRO organization needs to have a license. And I don't know, means you might be knowing or not, but MRO on its own is a very big industry. The current cost or current business revenue in the MRO business is somewhere around in the excess of 180 or 200 billion dollars. So it's a very big business for the MRO, right? And you would not believe most of the OEMs are also involved in the MRO, like Airbus, Boeing, and operators are also involved in the big businesses in the MRO sectors. Like, for example, Lufthansa or Air France, you might have heard about their airline services, but they are also providing the MRO services to other organizations or other operators. Similarly, we talk about system solution providers. So, for example, we are I am from Eaton. So Eaton is also providing system solutions to OEMs, right? So when we are providing system solutions, we have designed the product, so we have a capability also to repair them, and that's why we are also called as MRO facility as well. So just wanted to make sure that MRO is just not an organization which is just has set up their workshops at a hangar of any airport. They are basically OEMs can also do the MRO services. Suppliers like us can also do the MRO business, and we call it as a repair station because we have built the product, so we can do that. But we are driven, or everyone is driven by the regulations, right? So that's what I wanted to make sure that we understand, because this is a kind of a we want to just know what are the nitty-gritties within this MRO organizations that has been ensuring the upkeepment of a aircraft for airworthiness. Okay, so it's just not about fixing the issues; it's also about enabling the uptime of the systems to maintain it. Now, I will means so any question till now, like means, do we have any questions for MRO in general on the introduction part? Okay. Moving on to, so as I said, aerospace industry is a very regulated industry. So the FAA, Federal Aviation Administration, from the US, they have rolled out this Code of Federal Regulations, Title 14. So within that title, Part 145 drives the regulations for maintenance and repair processes. So that's why, as per the their terminology, any MRO facility is called as repair stations, right? And as I said, Eaton being a OEMs for multiple LRU systems in aerospace, we also get a automatic license for being a repair stations. But in general, what I wanted to make sure that we understand is like there are different types of repair stations based on the segment of the systems within an aircraft. So for example, we when we talk about airframe, so it is just about the body of the aircraft, from nose to tail. Okay. Then when we talk about power plant, so it's mainly to do with the engines. Propeller, so it is to do with the propelling systems, which basically takes the power from the engines and make sure that enough forces are available for aircraft to fly. Then radio sections, instrument sections, accessory sections. So every sections has they are classified as a different types of repair stations. So based on the whether it is a MRO based at an airports hangars or based at out of suppliers, and based on these types of systems, there are different types of air repair systems. Okay. Now, before going into and getting the advantages of MROs for a design engineer, I just wanted to give a brief about how a typical MRO organization functions as a process, right? So, is my screen totally visible, or is this screen is coming up? Should I make it
visible, sir? Visible, sir.
okay? Okay. Yeah. So generally what happens is, whether it is a MRO or repair station at a supplier end or at a airliner end, what happens is, as soon as a part has been failed or flagged as a failure from the aircraft, it has to be sent to the MRO facility, right? So MRO facility receives it, and the first step is that they do is that whatever the reason for the failure or the removal was mentioned by the airline operator, they will simply confirm it by testing it. Whether, for example, if there is a pump and they are saying that pump is not performing up to the mark, or it is not providing the enough pressure or enough volume, so the same thing will be tested and confirmed by the that is the first step within the MRO organization. And what they do is, if as per the complaint those failures are not replicated at a confirmation test, they will not proceed ahead. They will simply say that this product is having no fault found, no fault, there is nothing wrong with it. They will return the product to whoever this was the airliner or whoever sent the part. And if there is an issue with the product, they will just go to the next step. So next step is basically by looking at a product's status, they will be able to estimate the cost of a repair, like how much is going to be a cost for the repairing the system. And typically what happens is, there is a terminology called BER. I hope everyone is aware about the BER. So BER is nothing but a beyond economic repair. So that tentative cost of a repair, the MRO organization will come up with a invoice kind of a thing, or potential cost of a repair. And if so generally, typically what happens is, if the cost of repair is somewhere around 70 or 75% of the original cost of a brand new product, then they will call it as this is a beyond economic repair. So definition can vary, like whether somebody can call, like, okay, if a pump which is costing for me is $20,000 and repair cost will be $10,000. So it is a 50%. So they can take a call whether to repair or not. So for them, so it depends upon whether the customer, in this case the airliners, they want to get it repaired or not. So that is a very important step before going ahead and doing the maintenance or repair process. So this is a very important step that is done. In this case, customer is basically checking the repair invoice, and whether they accept or not. So if they accept, then we will go to the and proceed to the repair overall process. But if they don't accept, then again there is a two thing, whether customer wants to us to send, means us when we are repairing it, whether they want to send back the product as is to them, or they want to scrap it. Because what happens is sometimes even customer knows that the product is very old or it has gone beyond repair, and we cannot salvage it, so let's say scrap it. So they will give us a confirmation whether we want to throw it out or send it back to them. So both options are there. Okay, so that will be a typical process. And then as I said, if we have already got the go ahead for the repair, we will repair the product, reassemble it again, and complete the inspection or the testing whether it has now being up to the mark with respect to the performance and functioning, and then we'll send it to the customer, in this case mostly the airlines or whoever has sent that product. So this is a typical process flow, product has been removed from the aircraft, gone through the whole MRO process, and then sent back to the operators or customers. So any question here in the typical process flow for the MRO? Okay. Yeah, it was quite evidently easy as a typical process, but now second. Yeah. So now that portion comes wherein I want to just make sure that we are getting the understanding how MRO can help design and development. So typically we know that as a design engineers, most of us are aware about DFX approach, right? When we talk about designing a pump or a valve, or let's say an actuator, so we go with a complete design cycle in terms of we think about whether our product is, means whatever the design we are coming up with, we apply these 6 principles, right? Whether whatever the product we are designing, it is good for manufacturing, means there is a manufacturability or not, will it be meeting the design for reliability requirement, will it be longing last, and what kind of issues may come in the future, what kind of basically availability it will provide, how much quality we are bringing into the design of a product. Then we also think about how a product is going to be maintained, right? So those maintainability philosophy also gets included into the design philosophy. Then sustainability part of it is also important. Sustainability can basically captures 2 things. One is the availability of the parts or the components within the component or the part or sub assemblies basically, and also sustainability in terms of environmental effects, whether you might have heard about REACH and RoHS compliance for the aerospace products, whether it is a lead free component or not, those kind of things. Then also design for assembly, whether it is going to be easily assembled or not, assembled and disassembled for maintenance purposes. So those things are basically taken care. But you might not have heard about this thing like design for service. So design for service is also a very important aspect that design and development process should include. And basically, what do we mean by services? So if you go by a typical dictionary definition of a service, so it's basically says that it is an act of performing routine maintenance and repair work. Okay, so uh, if we are not including the design for service element into our design process, we'll definitely miss some of the things. What will happen is that the design processes that include the design knowledge, process knowledge, as well as the product knowledge, both the knowledges we use during the design process. But if we ignore the design for service element, we will be definitely struggling a lot. And why we are saying is because, as I mentioned initially, that MRO business is a big business. It hampers in a lot of ways. You might not be knowing that uh, within an MRO facility, sometimes they manufacture the product as well, right, to replace some of the components. Nowadays they have some licenses wherein they can manufacture the small parts and plug in those parts into the main product. So they also need to think about all the design principles and everything. So, and their learnings are basically going to help in overall design process. So that's why design for service is an important element nowadays, where engineering organizations are thinking about it. And design for service is nothing but learning from the MRO practices. Okay, and to s- to show the same thing here, basically what happens is how the design for service helps in a design processes. So basically what happens is when we are having this MRO facilities or services, we are providing the services, we kind of get the knowledge about the product. And what kind of these processes are like, if means that when we are running the fracas, or part rejection has happened, or we have a part life database from the field experience, then overall shops repair reports, those things, basically quality reports, FMECA sampling reports, everything. Basically it's a kind of, because in each of the steps we are doing some kind of a service or repair, right? So these service knowledge are getting accumulated, and it helps design engineers in four ways. Basically what happens is it helps to understand that whatever the requirement was set for designing a product, or and we had thought about this will be the function of this product, whether those functions were being performed by the product and with a expected mode of duty cycle or use, right? Means how the product was supposed to be operated, whether they are using accordingly or not, means whether they are abusing it badly or they are running it as per the intended cycles. So those kind of things we get from doing this service knowledge, getting the service knowledge. Then over a period of time, what kind of a degradation has happened into the product, that mechanism of degradation has as a benefit, which will basically help in design team in improving the design in the next iteration, or improving the product itself. Okay, then the not only the mechanism, but we also will know what are the causes and effect, which will again help us in improving the design, in terms of making sure that we are preventing those causes, or providing those information to the operators or the user, that these need to be used by these ways. And then knowledge of method of repair. Again, method of repair helps in a way, like if we know that how the repair organizations are repairing it. You might be knowing that repairs or maintenance happens as per the component maintenance manuals, right? In aerospace, all the products are sold with a CMM, we call it as a component maintenance manual. So those maintenance manuals are there, but whilst doing the services, sometimes those methods are getting also improvised, right, in the field. So those method improvisation again helps to the design team, in the improving their design and also improving these component maintenance manuals as well into the next iterations. So so that's what I was trying to make a impression here, that as a design engineer we should be taking a lot of help from the MRO practices, because they are going to help in a design in this way. Like we are getting a lot of service knowledge, and that will help us to improve the design and development. And in this slide here, again re-emphasizing the same thing. Typically, even if you don't talk about MRO facility, even you talk about a simple repair station as well, there also we can very easily identify. You might have seen that what is the main failure modes that is driving the failures of a product over a period of time, so we can identify those and include in our next iteration. So MROs are a very good way of providing the root cause analysis, actual reason for the failure, actual issues in the product. Then uh, then there is another thing called failure rates or reliability estimates. So most of the users, they want a very highly reliable product, and how to judge that is basically identify the failure rates with or identify the reliability, or MTBF. You might have heard in the aerospace business that most of the uh, industry stakeholders, whether it is OEM or operators, they talk about in terms of reliability that they want a very good high MTBF, right, or MTBUR. So MRO businesses helps in doing this failure rate estimation, because what happens is when you are in a design and development phase, you will use handbook data approach or some legacy information to come up with a estimation of the reliability. But if you are involved with MRO business, whether on your own, if you are having your own MRO organization, or if you are having a connect with MRO organization, then also you will be able to get most of the very great details, because in aerospace, except the critical components like engines or avionics, nobody even bothers to report out every failures into the aircraft to each of the stakeholders, right, whether who is the supplier, who is the OEM. They don't even feel obligated to report those out. So it's a very difficult thing. So when we are working in an MRO organization, or we are having a connect with MRO, it helps to identify the reliability of the product. So that is one of the advantages that basically helps us to, because once we know the reliability, then we can take a call whether we are providing a very high reliability, and can we go out and see an opportunity to monetize the reliability in terms of offering some different just like extended warranty case of scenarios, or if our reliability is not good, then can we improve the product. The other way would be like, if our products are highly reliable, but customer does not need those kind of reliability, then can we reduce the cost in terms of cost out projects you might have heard about. When the product is very highly reliable, let's go for the I will say not cheaper, but low cost designs, right? So those kind of options are available also, always. But for that, you need to have a reliability estimation, and therein this repairs systems helps a lot. Okay. And the third part would be like product improvement. So yeah, so basically root cause and failure rate estimation, ultimately they lead to a product improvement, and based on our service knowledge also we improve the product, right? And if we basically perform very good repairs, or we understand the issues of the customer, then we resolve their issues, and it helps in better customer relations. So this is basically MRO is helping engineering organizations in that way. And benefits to business, as I said, we would be able to have a very good product reliability. Any organization which is getting help from the MRO practices, they will definitely establish their own brand. Market share growth is very important. As I said, this MRO business is a great aftermarket business in terms of money making business. Lower warranty cost will be there for if we know how our products are performing, and we improve our MRO practices, and then that basically helps us reduce the warranty cost as well in terms of improvised products. It also helps in inventory management, like we know that if we are having complete control over the life cycle of MRO processes, then we know how much inventory to be maintained, and how much uh, production we need to ensure that we are making sure that all the parts are available. And additional service revenue, there are lot of service models which helps in getting the again mm, uh, benefits to the organization. Now I just wanted to give a so till now we understand like how MRO is going to help a design engineer, what are the benefits of a uh, MRO to the organizations, companies, as well as the design engineers. Now I just wanted to give you a glimpse of current technology and the future technologies that are there, which are basically utilized by the MRO facilities. So as we had seen in this slide, like this is a complete MRO process flow, right? So how this MROs are doing the or improvising their processes currently, and what are the different technologies that will help to improve MRO services. So here just I wanted to give a brief about that. So for example, currently some of the European MROs are using augmented reality glasses, augmented reality projections. So basically, when they are performing the repair processes, so the glasses, that augmented reality glasses they will use, they will simply get all the processes and steps, because instead of looking at a component maintenance manual, a paper driven report to follow all the steps, they will simply those glasses will project the each and every step, and that will be kind of improving their processes, reducing the time and everything. Similarly, some of them are using augmented reality projections. That is one of the ways, like it is similar to the reality glasses, but in terms of, instead of us having a small glass window wherein we can see the processes, big projections are there on top of the product itself, where we are maintaining that whether we are opening an engine or a pump section, those things are projected there. Then virtual reality is also one of the things. So virtual reality is like for example, if you have seen aircraft wheels, right? So I don't know, means do you have any information regarding, after every I will say 200 or 300 landing and takeoffs, they check the wheels, or basically when they maintain, means open the wheels, so they will remove the tire and then just simply take that metal wheel, and check for the cracks within the wheels, because it is very important that before they know that wheels are such a reliable product, that during the takeoff landing, if wheels are having a crack and it breaks, then it is going to be a catastrophic condition for an aircraft, right? So we have seen in the MRO facilities earlier, people used to use like this fluorescent materials, or dye, simply dip the wheels into a I will say a tank of a dye, and then through using some lights they will monitor the cracks. So those kind of practices were there. Now with help of virtual reality, those cracks are very easily to be identified. So this virtual reality is one of the tools that nowadays hangars are getting used to for improving and identifying the cracks and issues with their products. uh, the another way of using a technology is like a voice guidance. So we know that following the steps by reading the something from a projection or looking at a glass screen. If somebody provides a voice command like steps, they will ask some questions that okay, follow this step, and have you seen any issues with the product. You will respond, and that way it again improves the steps and alacrity, and I will say agility within the MRO services. So that is one of the things that nowadays they are using. Similarly, yeah, tablet application is nothing but just replacing the paper uh, paper driven CMM documents. They are simply looking at a tablet. So again, the from a cost wise, this virtual reality or augmented projections or reality glasses, they are costly as compared to the tablets. So most of the organizations are using the tablets nowadays. But yeah, these are all the other options that some of the good MRO organizations are they are using for improving the now the question you may ask like why MROs are doing this improving the processes. What is the need for this? So basically the need for this is that they want make sure that their processes are flown in such a fast manner so that availability of the aircrafts is maintained at all the times. So since due to the air mobility, increased air mobility across the globe, most of the time operators are looking for maximum utilization of the aircrafts, and for maximum utilization of the aircraft, upkeepment of aircraft is very important. So inventory management for the subcomponents, then completing the repair maintenance processes very fast is very important, because believe it or not, but single 2 hours journey of a flight journey, a ticket is like maintenance cost is uh, assigned somewhere around 20% of a dollar, so like 20 cents. So 20 cents is the cost of a maintenance per for a 2 hours flight, that is basically borne by the operators. So they want to make sure that these kind of maintenance costs are reduced, and to reduce, one of the one of the ways is to have a very quick turnaround time from the MRO's facilities. So that is one of the reasons that these organizations are looking for these implementation of current technologies, and also looking at the future technologies. Digital twin, I believe most of you have already heard about the digital twin. So digital twin is basically getting used a lot in MRO businesses. So we know that there will be one virtual prototype of our product, and the one will be the real product, which is basically flying in the aircraft, right? So the digital twin concept, basically what happens is that even before aircraft has returned to the hangar or the product has been removed from the aircraft, since digital twin, the virtual model of the original part is at the MRO facility, they will simply come to know what is the issue. So they don't have to be even looking at it, or looking at the failure reports. They will simply be able to know that, and they will use that digital twin technology to repair the product very early, very quickly. And the other aspect of digital twin is like the past experience, the latest experience of this repair is going to help me in the next repair as well, or the next aircraft which is coming. We know that okay, similar product are coming, so we know. So it's basically it helps in continuous improvement in the overall processes from a repair perspective, or operation overall perspective. So that is a very beneficial technology that MROs are exploring. They have not implemented it, but these are the technology that they are going to implement, or they are looking at it. Similarly, additive manufacturing. So additive manufacturing is one of those that technology why MRO wants to use is as I said earlier, that for some of the smaller components, MRO facility wants to manufacture those parts. So additive manufacturing is that process wherein if you are not a mass production company, you just want minimum number of products, a very low product, a low quantity of a product with easily available. They don't want to be dependent upon the OEMs or the suppliers, so they just want to quickly manufacture it. So this 3D printing technology is getting accepted a lot, and I can definitely tell you with the information that I have that you would not believe Lufthansa Technique, which is a MRO facility. They have a very great facility with them for additive manufacturing, which is basically they are just using for replacing the parts, sub assembly parts within the big components. So it's a really great thing that has come up. They are using it a lot, additive manufacturing. The next technology would be like autonomous drone inspection. So this is one of that things. So this is used mainly for the complete body inspection of an aircraft. So aircraft being a very big, if they go with a traditional inspection of an aircraft, like aircraft's airframe inspection, it takes a lot of time, and there is a lot of issues, or there is a lot of vulnerability in getting incorrect information, because proper things cannot be done. So what happens is autonomous drones are getting used nowadays. So as soon as aircraft reaches the hangar, these drones are flown around the aircraft, and they keep capturing all the information through the cameras and all, or all the scanners, and they provide the details to the facilities where they are airframer repair stations are using this a lot. Not exactly they are using, but they are exploring this to use, and some of them have started using. These technologies are, I will say, mostly are getting used in Europe. I don't know whether Indian MRO facilities are going to be adopting this technology, but Singapore MRO facility have started doing some of these things. Then the last technology I wanted to bring about was roof or hangar entrance scanning. So if you see from this image, as soon as aircraft starts entering from the gate of a hangar, so at the top of the gate of hangar there will be a lot of scanner. So it will simply throw the lights onto the aircraft, and complete aircraft will be scanned out, and that is going to be used. That there are some proposals for by some of the MROs that they are going to use this roof or hangar entrance scanning technology. So these are some of the technologies that I just wanted to give a brief about. So any question on this thing that is going to be used by MROs nowadays? Anyone?
I have one question.
Yeah, please.
This wheel check you were mentioning, right? Is that a check?
Yes, it's a kind of a check, because I think if you remember, generally what happens is a check, they take 200 or 300 flight cycles, right? So
Okay.
they do that during the A checks. But there is another thing, like it depends upon the OEMs also. If OEM has instructed to the operators that you can wait for the B check also, but again it has to be coming from the OEMs, whether the kind of wheel materials they have used, it is suitable for waiting for the B checks or even A checks. So earlier they used to go definitely for A checks. Nowadays they are thinking to go for the B checks as well, because they have improved materials laws a lot.
Yep.
But yes,
Another
it is
question.
mostly, yeah.
Another question. This design for service, whatever you mentioned,
Yes.
is including maintenance also.
Yes, definitely. Yes. Design for service is basically that terminology is coming from a maintenance itself. Like when we are maintaining the products, so we know that what kind of issues we are facing, right? For example, let's say talk about a pump. So when we are maintaining the pump, we know that when we are disassembling the pump and then assembling the pump, what kind of
Accessibility.
accessibility issues are there, but also components like o-rings. We come to know that okay, these o-rings are not good for this particular airlines, because these airlines are flying in a very hotter atmosphere. So they can definitely, means even though OEMs had decided that for this kind of flying zones you need to use, I mean they will use that kind of material, but how that has come to be to the information to the OEMs are basically using these things, service knowledge. So when they do this kind of servicing, they understand like okay, in the cooler zones these kind of products are lasting longer, in the hotter zones these are lasting less, so let's change the material. Okay, those kind of decisions are getting taken through the use of the service knowledge. Yeah.
Yeah. My point was, I mean, more of like, one is salvageable thing, whatever you mentioned,
Yeah.
design for service. Other thing is like human engineering, for example,
Mhm.
the accessibility in the engine, for example, you may have less space.
Yes.
Tools that
Yeah.
we use,
Yeah.
whether
So
they are
that is basically part of your design for maintainability, right? So if you think
yeah,
about,
correct.
yes,
So
so
that is,
design for maintainability basically takes care about these things, whether is it accessible, or will there will be need of a special kind of a tooling, means on a very easily normal spanner can reach out to the component to tighten the screw or remove the screw, or we need a special tooling. So that is there, but again service engineering also helps in that, because what happens is these MRO facilities when OEM has designed the product and they designed the aircraft looking at all the maintainability aspects, so they were okay that okay, this will be good. Now when MRO facilities are maintaining them, so if they are improving their processes by learning from their experiences, so they feed this kind of information again back to the OEMs, because we can definitely, you can come up with a different solution which will not only help you but help us also. So those kind of a to and fro communication is basically the part of design for service.
yeah. Thank you.
Yep, thanks. Yeah, as I said, we just discussed a lot about benefits of the MRO, but there are some challenges as well. And typically there are three kinds of challenges in MRO practices, and they are kind of linked to each other. So what happens is data quality is not good. So most of us know that there is a an aircraft, they might have more than 5 lakh parts, right, in an aircraft, more than that parts in an aircraft, and not everything is critical in terms of safety, right, like engine or avionics components or landing components, but some of the in between the components who are just simply for achieving something, some functions, nobody tracks the information with that for those parts, and that is wherein this is a one of the biggest challenge. For example, the operators who are using the aircraft, they will not provide enough details for the product, that how they have used, what they have done, what was the real reason for removal. They simply say that it failed, we are sending it for repair, right? So those kind of data quality issues are always there. That is the biggest issue in MRO organizations. Then the next is basically lack of rigor by the user for data monitoring. That's what I was saying, that if it is not a safety critical, they simply don't follow the rigorous processes to monitor that. Okay. And then effective data management during the repair process. So again, that is at a end of a MRO facility. So what happens is that if they are not following the rigorous management of a data, like what happened, and you would not believe 10 years back people were still using a paper, wherein they will simply note down. Even in this age of a computerization, and they still don't because they simply say that okay, this is the computer station, it has to be placed at somewhere else, and we are having where we are opening the parts, it is totally greasy and messy, so they don't follow the complete information that they track. So these are the some of the typical challenges that MRO organizations face, whether it is a repair station at a supplier end or whether it is a MRO at an hangar end. But these are the issues that are involved with the challenges are involved with the MRO business. Yeah. So overall, till now, that's what I wanted to give a brief summary about this session. Like we have covered MRO introduction, typical process, benefits in design, development, and engineering, current and future trends in terms of technologies that are getting used in the MRO, and challenges. So yeah, that's what I wanted to cover. Any question or anything you want to ask on the session? Because I have references, you can use these references for further studies, detailed studies. I have used means I have referred a lot of FAA guidelines for regulations and understanding the MROs. You can go through some of the papers here. Basically, the design for service model or servitization of the business. There is a very good paper written by S. Vandermeer, so you can use that one. Yeah. So that's all I had.
Any questions we have for Jitendra?
Hi, Jitendra.
Hey,
Yeah, that was a good presentation. But anyway, this is Greek and Latin to me because I'm not from this background.
okay.
But anyway, I have one question.
Right.
So you said this repair and overhauling will have any kind of frequency that is for incoming and then outgoing. So we'll be having any frequency for
Yes.
having this MRO.
Yes. So typically, there is no regulation as such, but if you read through some of the literatures, you will find that typically there are three or four kinds of checks. So there is a terminology called A check, B check, C check, and D check, right? So A check is typically that when an aircraft has accumulated or aircraft has flown for, let's say, 200 or 300 flight hours or 300 cycles, right? So 200 hours or 300 hours, that is a basically typical range, which means Airbus will provide a different range, Boeing may provide different range, and for different types of aircraft, for A320 or 737, they will provide different range for doing the A check. For other aircraft, they will provide a different range. But based on their the way aircraft industry or aerospace industry has evolved, accordingly they have come up with this scheduled maintenance checks frequency. So A check is typically this is a very early check, that is called as A check, where we are talking about 200 to 300 flight hours. Then we talk about B check. So the B check is somewhere around within one year, so 12 months, right? Then so and again, these checks are also very they vary in terms of I will say criticality in terms of like A check is minor checks, right? Simply they will simply see the things, see the parts and all. B check is wherein they will do more detailed maintenance or more detailed inspection. The C check is typically 2 years check. So either 2 years or 5,000 or 6 hours, 5,000 or 6,000 hours flight hours. So if an aircraft has run for 5,000 hours or 6,000 hours or 2 years, whatever comes first, so they will do the C check. So see, in the C checks now, an aircraft will be completely opened and they will go in each and nook and corner of an aircraft, look for every component and do the, as per their maintenance procedure, they will do the complete maintenance. And then I think D checks, they go for 5 or 6 years in service. So yeah, but these are not regulated numbers. These are always driven by the OEMs.
Okay.
Yeah.
Okay, great. Thank you.
Yeah, thanks.
Any other question? I think what we will do is after this session, I think from SA India office we'll receive an email regarding the contact details, so you can connect back with the presenters if you have any further questions. Ilango, can we also send out a survey also link so that we can
Sure.
get feedback from the participants?
Sure, sir. I will, yeah, usually we will send the feedback form
Yes.
along with the certificate to our participants. We will send it, sir.
We request you all to fill it up so that we keep improving. We see that will help us keep improving the sessions, and you can also let us know if any other topics you want to add over there. We can further include that. Yeah.
Yep.
Thank you, Jitendra. Thank you, Pawan. Thank you for
Thank you,
your.
thank you, everyone. Have a great day.
Yeah. Thank you. Thanks everyone for listening patiently and good questions. And it was great for me to have this opportunity. Sandeep, Ilango, yeah, thanks a lot, and everyone.
Thank you all. Happy weekend. Thanks, Ilango, for
Thank you, sir.
arranging this all.
Thank you. Thank you, sir. Thank you.
Thanks, Ilango. Bye.
Thank you, sir. Bye.